Alright, 12 for limits at infinity and limits of sequence. Actually fairly straightforward. Our job here is to figure out what happens to functions when numbers get really, really big going towards infinity. So, two things for this whole chapter, right? First one is finding tangent lines, which we figured out in 12.3. That's what 12.3 was all about. And then finding the area of a region. So that's what we're going to jump into, starting with 12.4 and then really get into in 12.5. But before we can get into that, we need to be able to do the limit at infinity. All right? So what that means is what happens to a function as the numbers that we plug in for x start getting really, really big going towards infinity. So let's use this function to start, x plus 1 over 2x. All right. What happens if we graph this thing? If we graph it, it looks like this. And notice that it has an asymptote with the line y equals a half. All right? And that as we go really, really negative, we're going to get really close to that line. And as we go really positive for x, go way out here, we're going to get closer and closer to this line. All right? So what's happening here is we're finding a limit. The limit as we go to negative infinity is a half. The limit as we go to positive infinity is a half. So the limit as we go towards infinity is a half. All right? So the limit means that the value of f of x gets arbitrarily close to a half as x decreases or increases without bound. That phrase there, decreases or increases without bound, means as we get closer and closer to infinity, which of course we can never reach, so we're going without bound. We're never stopping. All right, so this is how we write it, and this is the key part here as we go towards either negative or positive infinity. And then we have some helpful little hints here, and this is the key. If we're doing a fraction and we have a number x is going to infinity, if we're dividing by that, 1 divided by a really huge number, we're getting smaller and smaller and smaller and smaller. So eventually we're going to hit 0 if we were ever able to get all the way to infinity. So if you have an x in the denominator to any power, the limit of that is going to be 0 as x approaches infinity, and negative infinity as well. All right, so we're going to use that here for the first example here. What's the limit as x goes to infinity of 4 minus 3 over x squared? All right, so as our numbers for x get really huge, right, we're going to have 3 divided by really, really big numbers, which essentially becomes 4 minus 0. Because if we're dividing by a huge number, it's going to turn into 0. So our answer here is simply 3. All right. Now we could graph this and take a look at what the graph looks like as well, just for verification purposes. So y equals 4 minus, in parentheses, 3 over x squared. I'll close my parentheses and graph this. All right. So as we go towards infinity, this line right here is y equals 3. We could put another line in there just to prove that that's true. And there's the line y equals 3. So it's going to start folding back down to the, whoops, it's going to be 4, isn't it? Apparently I can't subtract. 4 minus 0 is not 3. 4 minus 0 is 4. Wow. Apparently it's one of those days. 4 minus 0, 4. Not 3. Let's graph that again. All right, so this is why we can verify via graphing and clearly see the mistakes that we make. How about this? Hey, there we go. We're getting close to the line y equals 4. All right, so do what I just did and do your algebra correctly and see what you get for the limit as x approaches infinity of 3 over x squared plus 1. All right, so let's take a look at some slightly more complicated examples here. Let's look at this first example A, negative 2x plus 3 over 3x squared plus 1. All right, so as x gets really, really big, negative 2 times a billion, that plus 3 really doesn't matter anymore. The difference between negative 2 billion and negative 2 billion and 3 is very, very small. All right, same thing here, 3 billion squared. All right, the 1 really doesn't matter. And here's the key. We're squaring a billion or squaring a trillion or a gazillion. X is getting really big. if we have these and the 3 and the 1 don't matter anymore, x versus x squared, what's getting bigger faster? The denominator is getting bigger faster. And we found from the last ones that if the denominator is getting bigger faster, we're going to have 0. All right, what about this one here where the degree matches up? All right, so we're always going to cancel those out. When we get really big, the 1 and the 3 don't matter. So ultimately, the key here is the -2 and the 3, because x squared and x squared are going to start canceling each other out. So the answer here is -2 over 3. All right, and lastly, what happens if the numerator is winning? All right, the numerator is getting bigger faster than the denominator is. We're just going to get bigger and bigger and bigger and bigger and bigger, right? Well, eventually, just keep going. We'll get to infinity, which we say there is no limit because we're increasing without bound. All right, and so same thing. Exercise 19. See if you can figure out what the limit here is. Okay, so here's just a quick summary of that. For the limit, if the numerator is smaller than the denominator's degree, the answer is 0. If they're equal, we divide the leading coefficients. And if the degree of the numerator is bigger than the degree of the denominator, the limit does not exist. All right, let's take a look at a word problem here. We're manufacturing greeting cards at 50 cents a card. Initially, we got to pony up $5,000 just to get going in this business. And so then we have a cost of 50 cents per card plus that original 5,000. If we figured out the average cost of the card, we would divide by how many cards we were making. All right, so let's figure out what our average costs are. So we've got 50 cents times 1,000 plus 5,000 over 1,000, and then we would plug in 10,000 and 100,000, etc. Instead of doing this by hand, let's use our good friend the calculator and the table function. So we've got, in parentheses for the numerator, 0.5x plus 5,000 divided by x, and we'll go to our table, but let's put it in ask mode so we can plug those numbers straight in. And so the first one we want is 1,000, and the average cost per card is $5.50. So for $1,000, that $5,000 initial cost really matters. What if we made 10,000 cards? Oh, now it's only $1 per card, so things get a lot cheaper there. As we keep increasing up to 100,000 cards, now we're down to 55 cents per card. All right? If we keep increasing and increasing and increasing, what's going to happen to our average cost? Well, look at our degree. The degree of the numerator equals the degree of the denominator. Eventually, we're going to end up with an average cost of 0.5 divided by 1, or 50 cents per card, if we could keep going to infinity. So the limit as c approaches infinity is going to be 50 cents. All right, so use the same thinking here for 55. Okay, so limits of sequences. Sequences behave just the same way as our just normal functions. So if we have a limit here, and limit of a sequence, as long as it's getting smaller, then it's going to converge to 0, and we can write our limit here. All right. Otherwise, we've behaved the same way with checking the numerator and the denominator. So right here, the answer here for A is going to be 2 over 1, or 2, since they match up. Here, we're going to say the denominator wins, so our answer is 0. And in this case, we're matching again. 2 over 4 is 1/2. All right. So, quickly, see if you can do 39. All right, last one here. So, finding the limit of a sequence. And so the key on this, what this is saying is get yourself into standard form, which means multiply all the way out. And you really don't only have to multiply all the way out for the leading terms, too. So let's take a look at this. On the top, we've got n times 2n times 8. So that's 16n cubed over 6n cubed. So our limit as n approaches infinity is going to be 16 over 6, which is 8/3. All right. So don't need to FOIL all the way out because we really only care about the leading terms. So wrap this up. See if you can figure out 49. Fill out the table to confirm. And your job here for 12-4 is done. Any questions? We'll go over these in class. Good luck.